Oke, bisa saya mulai sekarang ya? Oke, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen, and also very good morning for those in Portugal. Thank you for joining the Focus Group Discussion Volume 6 organized by Institute of Research and Community Service, LPPM, Institut Teknologi Bandung. My name is Kiki Adi Kurnia from Chemical Engineering Department. I will be the moderator for this event. Before starting the discussion, I would like to invite the Chair of Institute for Research and Community Service, Dr. Yuli Setio Indartono, to deliver the opening remarks. To Dr. Yuli, time is yours.
Of course, thank you for Professor João Manuel Costa Araujo Pereira Coutinho. I'm sorry if my spelling is not correct, Professor. But I'm very glad that you are here with us. Good morning for the European country, I think, and good afternoon for all audiences in Indonesia. Yes. So, in my understanding, we have a close collaboration, Professor Coutinho, between Institut Teknologi Bandung and Universidade de Aveiro through Erasmus Plus program for staff mobility between two universities. So I think this webinar, the FGD, is quite important for us to strengthen the collaboration between ITB and Universidade de Aveiro. And for the audiences, I think the moderator will also introduce Professor Coutinho is a very well-known researcher, scientist, having very high H index of 88, with more than 700 articles in various high-impact journals. That's why the topic today about the CO2 capture and conversion with ILs and DES, how to make it work. I think this is quite important because will be delivered by the well-known researcher and scientist from the top university in Portugal. So on behalf of Institut Teknologi Bandung, we are very thankful to Professor Coutinho for giving us this quite important lecture. Thank you, Pak Kiki, for the time.
Okay, thank you very much, Dr. Yuli, for the opening remarks. Ladies and gentlemen, today we are very fortunate to have Professor Coutinho as our speaker in forum group discussion. As mentioned by Dr. Yuli, Professor Coutinho has published more than 700 articles with current H index of 88. It is very excellent achievement for scientists. He has published in high impact journal, and recent publication he published in Green Chemistry, one of the top tier journal, as well as in the fluid phase equilibria, also in SCS and Chemical Engineering journal. So today he will deliver the talk on the CO2 capture and conversion with Ionic Liquid and DES, how to make it works. To all audience, I kindly ask your cooperation to turn off the mic. Maybe later during the discussion, when you have any question, you can open the mic again. To Professor Coutinho, time is yours.
Thank you, Kiki, for this kind introduction. Thank you, Professor Yuli, for introducing me with my full name. That's something that very few people are aware of and use. Myself, I seldom use it fully. And yes, indeed, you pronounce it very correctly. While I was I guess I have to share again the presentation, right?
Yes.
Okay, there it is. Well, I was the prorector for the University of Aveiro. That is a position that I resigned a couple of months ago for another thing that I will show you in a minute. I was very interested in developing the collaborations with Indonesia. I had the opportunity to visit a number of universities, unfortunately not ITB, but we signed agreements and we managed to have these Erasmus Plus ICM grants so that we can have mobility. I know that pandemics has been preventing mobility between our countries, but nevertheless, we managed during the pandemics together with Kiki to carry a number of seminars, lectures, courses between Aveiro and a number of partner universities in Indonesia, and do hope that in the near future we will be able to engage in physical exchanges of researchers and students, because this is very enriching for both parts. I've been working on this theme of CO2 capture for many, many years, and that's how I met Professor Cornea and invited him to join us in Aveiro with our lab. And that's what I will tell you a bit about today, the development of this last decade, looking into how can we use Ionic Liquids and epithetic solvents for CO2 capture and more than capture the utilization. This is a world map that I have in my students' room to convey this idea of internationalization. I have students that come from all over the world, from Timor, from Australia, from Brazil, from Europe. And this gives you an idea how far apart we seem to be, but truly distance today are rather meaningless, as we have discovered during these last 2 years. Portugal is in the westernmost corner of Europe. It's one of the small countries close to Atlantic Ocean. And you probably have never heard about Aveiro, but you probably heard about Lisbon, that is the capital, Porto, that is the second largest city. Aveiro is in the coast, close to Porto, 50 kilometers away. And the dots that you see here are the main universities in Portugal, and among them, the University of Aveiro. Aveiro is a picturesque town by the seaside, and I only hope that some of you can see these places live once you have the opportunity to visit us. The university is a very young university. It's among the youngest universities in Portugal. It's not even 50 years old yet. And the campus that I'm showing here, it's about 20 years old. You can see the sea down there, the lagoon by which we sit, and with the salt pans for the salt extraction and the fish ponds for fish production. But as I was telling you, I used to be prorector for internationalization, but these days what I'm working with is as director of CICECO. CICECO, Aveiro Institute of Materials, is the largest material-related researcher unit in Portugal, and it covers many different areas of materials and material applications, as you can see in this word cloud. And these are the main lines of work, and I myself and my group works on this area of biorefineries, bio-based materials, and recycling. CICECO has a worldwide network. More than half of our papers, 55%, are in collaboration with the international institutions. About 10% of the total papers, 60 per year, are with the top 50 institutions in the world from the Times Higher Education. And also not only the papers, but also we have a very international setting with about half of our researchers and students being from abroad. I myself have been working in this field of sustainability for many years. Different approaches, not only this one that I will show you today, but today is about how can we cope with global climate change? And as you know, most of the climate change and these days are the days to talk about climate change, not only because of COP26 summit that is taking place in Glasgow right now, but because it's really happening, and we feel it. We feel it as we felt it this summer, this scorching summer here in Portugal and Spain. And we know that a great part of it is due to the emissions of CO2 resulting from fossil fuels combustion. It's not only that, and one of the big achievements of this summit has been the recognizing of the importance of this, the methane emissions, not only human methane emissions, but also from livestock, and attempting at reducing methane emissions is also very important. But what concerns us mostly is the CO2, and that's what I will tell you about today. This is the idea of the CO2, as you know, it's not only to prevent these emissions, because it's hard to prevent these emissions, more how to capture once it's produced, and how to store it underground or in other techniques, or how to use it, making of CO2 a raw material to produce other things. And it's already being used to produce fertilizers, chemicals, and so on, but it could and must be much more used in the future if we develop the right techniques, not only to capture it, but also to convert it. In what concerns the capture, there are three approaches: the pre-combustion, the post-combustion, and the oxy-fuel combustion. As you probably know, I won't spend much time on this. Most people focus on the post-combustion approach. Once the CO2 is produced, in particular in large units like units where electricity is produced, or cements are produced, and so on, you can try to capture it and separating it from the gaseous effluent, and then try to use it or to store it. And our idea during these years has been to look into the development of new solvents for CO2 capture and sustainable process for CO2 capture. There are processes today for CO2 capture using amines, but these have a number of limitations that are well known for most of you. So the idea has been to develop these new solvents, and we've been looking into ionic liquids. And ionic liquids are salts that are liquid at low temperature, and because they are salts, they have very low vapor pressure. Essentially, they are not volatile. They have a good thermal stability, a very large liquids range, meaning that you can use them as liquids in a very large temperature range. But the most interesting property is not only that they can absorb large amounts of CO2, but they are designer solvents, meaning that you can try to design them or their mixtures to achieve the properties that you need. And they have been studied for many different applications. I won't go into detail of this, but one of them is clear, that the CO2 absorption. And that's what I will tell you about in the first part of my lecture. Can CO2 be used, ionic liquids be used for CO2 absorption? Well, this story starts with a Nature letter in 1999, so more than 20 years ago. It was really a lecture, a very small one, less than 1 page long, where John Brennecke showed that ionic liquids could be used to process CO2. And this declenches a whole new field of studies with growing interest until today. Today, there are about 500 papers a year on CO2 and ionic liquids with different aspects. And while the research on ionic liquids is leveling off in the last few years, the interest with CO2 and ionic liquids keeps increasing. We in Aveiro have been very early looking into that, and to look in ionic liquids as absorbents for CO2. Everybody in the days that we start working were looking into them as physisorption fluids. So you need pressure, and what we start by doing was obviously the thermodynamics of the process, the phase equilibrium. How much CO2 could you dissolve in ionic liquids? So we bought an high pressure cell that you can see here that has a piston at the end so that you can control the temperature. You can see here some tubes that are used to thermostat the cell, and the cell has a sapphire window at one end. One end is the piston, the other end is a sapphire window, and there is a camera from which you can see the inside of the cell, as you see here in the picture. Here you see three phases. It's typical of things with ionic liquid: a liquid phase, an intermediate phase, and the CO2 phase. But in what we use this is to measure the disappearance of the phases, and then to measure the phase envelopes, then the phase diagrams and curves like these that show you at a given pressure how much CO2 you can get inside of an ionic liquid. And in those days, that was 2007, 2008, people were looking very much into this type of fluorinated ionic liquids with imidazolium and measuring these curves. And they were apparently very promising because they seem to have very high solubility. Once we start this, I immediately start to think about how to design the ionic liquid. And the thing to design the ionic liquid to capture CO2 was obviously to think about the pKa of an ion. We would need, since CO2 is an acidic gas, we would need something that would have some basicity to interact better with the CO2 or to react with the CO2. And so we start looking into ionic liquids with different pKa, and to our surprise, the solubility did not follow the pKa values. We were expecting that the lower the pKa of the acid, so the higher basicity of the bases, but it didn't work like that. And things that were completely neutral seemed to work fine, while things that had some basicity seem to work worse because they have higher pressures. And this was very strange at the time. We couldn't really understand what was happening. And there was a paper from also Brennecke and a group in 2004 in JAX, where they tried to address why is CO2 so soluble in ionic liquids. And we start reading the literature. We start looking at our data and literature very early. Remember that first paper by Brennecke on Nature was from 1999. Tom Welton in 2000 was already saying that the strength of the interactions cannot be solely responsible for CO2 solubility in ionic liquids. And when we were doing this work, CICECO was publishing this very interesting paper showing that CO2 BF4 and PFC interactions were stronger than CO2 and TF2. And the CO2 and TF2 was apparently the fluids that could dissolve more CO2. And the strong Lewis acid-base interactions between ILs and dissolved CO2 has no promotional effect on CO2 solubility. That's exactly what we had seen with our measurements with the ionic liquids with different pKa's. So all these were very weird and bizarre because it was very unexpected. So we start asking ourselves, instead of why CO2 is so soluble in ionic liquids, whether CO2 is really very soluble in ionic liquids. And that's about that time also when the first report from IUPAC with reference data on ionic liquids appear. And this paper compiles a number of different properties for a common ionic liquid that a team was working with, an international team from Europe and from United States. And when they were looking into the CO2 solubility, that was one of the properties that they were studying, they were not looking into terms of mole fraction, but molality. And when this was published, we decided to try this to different ionic liquids, because in this paper, they only focus on a single ionic liquid, the C6-MIM NTF2. So we decided to look into all the data that we had collected and data from other people in literature and plot it in terms of molality instead of mole fraction. And to our surprise, and to the surprise of many people, the lines, the data, they fall all together in a single line, as if there was no difference between the different ionic liquids. And believe me, it was very, very, very difficult to convince the community of this result. And more than that, you see, there is one thing here that is not an ionic liquid, that is hexadecane. That is these green triangles. You can see these green triangles, they are sitting on top of the ionic liquid. So an alkane seems to have exactly the same solubility for CO2 as any of the ionic liquids. And that's why these results were so controversial at the time, because people refused to accept that we were saying that ionic liquids were not special to dissolve CO2. The apparent effect result more from the difference in molecular weight than in actually behavior. And that's what we tried to show, that with these results we could produce universal correlation for the solubility of the CO2 in ionic liquids. And we try to convince people showing this, that is, these C4 and TF2 were considered the best ionic liquids to dissolve CO2, and people believe that there was something special about the fluorinated part of the anion. So what we did was we picked another ionic liquid, that is this tetrahexyl tetradecyl phosphonium chloride. This is made essentially by alkyl chains, so no special interaction with CO2, and the chloride that has also no special interaction with CO2. And we try to show that this ionic liquid that should have no special interactions with CO2 was better, actually. You can see that the curves, the circles, they sit at lower pressures than diamonds, showing that the solubility is higher on this ionic liquid than in this ionic liquid. And this ionic liquid had no special interaction, meaning that it was really just a matter of the molecular weight that was leading people into the wrong conclusion that CO2 was very soluble in ionic liquids. Obviously, we have been studying this from other points of view and not just from the solubility, macroscopic solubility point of view. We, together with a group in Lisbon, have been looking using spectroscopic techniques into the CO2 solubility. This is Raman. We use also FTIR and so on. But what you can see here in pink is the spectra of the pure CO2, and in this case is trifluoroacetate, butylimidazolium. And then in green is the same ionic liquid when you pressurize at 85 bar the CO2. And what you can see is that the spectrum of the ionic liquid is essentially non-changed, with the exception of these two bands that are bands of the CO2, the pure CO2. These are the fermidiodes of CO2. So it is as if the ionic liquid is not seeing or not changed by the CO2, and CO2 is also not significantly affected by the ionic liquid. And you can see this also here. As you increase the pressure, you increase the CO2 content, and you just increase these two bars without displacement of these bands, meaning that there is no significant interaction between this ionic liquid and CO2. So the conclusion of this work was that the solubility of CO2 and non-volatile solvents is solvent independent, and we managed to show that this is true not only for ionic liquids, for alkanes, for methyl esters, and for many other compounds. Essentially, they all dissolve the same amount of CO2, and the apparent high dissolution was due to the molecular weight. And this was so contested that we had to go and to show this again a few years later, again picking the same correlation and establishing a benchmark that nobody could doubt about, because these were data very well established in literature for icosane. We create a correlation that you will see now as this solid line. This solid line is the icosane solubility at a given temperature, in this case 298, and this was a work that we did together with Kiki Cornea in those days. And you see that the red line is ionic liquids, and they are essentially the same at this temperature, and the ionic liquids, they perform poorly at higher temperatures because they have a stronger dependence on the solubility with temperature than the alkane. And well, there is this Selexol process showing that the oxygenated compounds are very good at dissolving CO2, and they are used industrially. So people start designing oxygenated ionic liquids and try to claim that they were tuned solvents for CO2, but actually, again, the full line is for the icosane. The red line is an average of all the data that had been published for the ionic liquids. And as you can see, the ionic liquids, even oxygenated ionic liquids, were worst with, and this is a caveat, we will be back to this later, with the exception of these carboxylate containing anions, where they are really improved ionic liquids in terms of the ability to capture CO2. People were also thinking about using mixtures of ionic liquids, and again, the mixtures of ionic liquids were no better than the alkane. Either they were just like the alkane as in this mixture here, or worse than the alkanes, with the exception again of systems containing acetate or any other carboxylate. And this is not surprising because, as a few years ago, Pepe Palomar from Madrid showed in a paper, when you have mixtures of ionic liquids and you want to enhance the CO2 capture, you have to have mixtures with positive deviations from the ideality, meaning that you have to have mixtures where you have unfavorable IL-IL intermolecular interaction. So you have to, again, ionic liquids are designed as solvents. Their mixtures can also be used to design the solvent, but you have to know how to design the solvent. And in this case, you have to strive for unfavorable intermolecular interactions. And that's what you can see here in this graph, that when the activity coefficient is positive, meaning that you have unfavorable interactions, your Henry constant decreases, meaning that you increase the solubility. While when you have favorable interactions, your Henry constant increases, meaning that you decrease the solubility. So designing mixtures of ionic liquids for CO2 capture means designing mixtures that have poor interactions between the two ionic liquids. And that's why, pardon me, that's why diputetic solvents do not work for CO2 capture, because when you design a diputetic solvent, you design something that is a mixture of two solvents that you may claim that they are not solvents because they are not liquid, but conceptually you have two compounds that interact very strongly with each other. That's the concept of a diputetic solvent. You create two compounds that interact very strongly through an acid-base interaction or hydrogen bonding. And as I just have shown you, If the two compounds, they interact very strongly with each other, they will interact very poorly with CO2. So these were the data that me, Pedro, and Kiki collect from literature in 2016. Today, there is much more data, but the result is probably exactly the same, because you cannot escape the basics of thermodynamics. If two compounds love each other, they tend to avoid a third one. So if they interact very strongly with one another, they don't want to interact with another thing. So to design a good solvent, you should not look for two things that interact well. You should look for two things that interact poorly. But this is not the only problem, as I've been showing, of ionic liquids. That is, most of them, and I stress, most of them do not have a physisorption, and I stress physisorption, that allows significant CO2 solubility. But ionic liquids have also another problem that is related with their transport properties. You know that water has a viscosity of around 1. You see, ionic liquids are 10 times, 100 times, 1,000 times more viscous than water. And if they are more viscous, all the transport properties are worse in ionic liquids than they are in other solvents. And that's why, if you use an ionic liquid, you recognize this problem of the viscosity very quickly. And that's why a couple of years ago, in 2018, Mota Martinez and the group in Imperial College, they decided to do the design of the columns that you would need to do to capture CO2 using ionic liquid as a physical solvent. And what they conclude is that you would need the columns that range from 150 to 800 meters. So basically, it was unfeasible to use ionic liquids as physical solvents for CO2. And I hope this paper and the results that I showed you clearly show that this is not the way to go. But this does not mean that you cannot use these fluids, because, and up to now, I've been showing you what not to do. And from now on in my lecture, I will try to show you how these things can be used. And how can these things be used? Well, what are the advantages of these ionic liquids? If the ionic liquids, if the diptyletic salts are not good to capture CO2 by physisorption, they can do other things. One of the things that they are very good at, it's selectivity. They probably are not very good or not better than the other fluids at capturing CO2, but they are much better than other fluids at separating CO2 from other things. And I will focus in particular in methane, because when we did these works, we were very interested in the natural gas and the separation of natural gas from CO2. And what we realized, and again, the line that you see here is the line for the CO2 solubility, and the dots are for methane solubility. And although some ionic liquids that have very long chains have a similar behavior, most ionic liquids, and in particular these that I showed you before for CO2, that follow this line, now they have a much different behavior for methane, meaning that you have very good solubilities, really excellent solubilities for methane. The lines that you have here are the lines that have been reported, two models that were reported in literature for the selectivities that you can use with the common solvents for the separation of methane and CO2. And the dots that you see here are dots for some of the ionic liquids that we study, where you really can improve, in some cases by almost an order of magnitude, the CO2 methane selectivity. So They are very good for doing separation. And this curve is also very interesting in another point of view, because it tells you how to design the ionic liquid. Again, the question of designer solvents. It tells you that if you use an ionic liquid with a very high molecular weight, it's not good to do the separation. You need to use short ionic liquid, and short ionic liquids tend also to be, as you would expect, less viscous. So you can also gain in terms of the transport properties. And that's what I show you here with actual data on this figure, where you have the methanol, where you have the amine, where you have the solvent that is used in the CICECO process, and you have a range of ionic liquids, and in particular the ionic liquids that we have been studying, that are far better at doing the separation. So all comes down again to this question of designer solvent and selecting the right solvent. But for that, you really need to understand the fluid and understand how the solvation of a given gas or a given compound takes place into the ionic liquid. Because once you know that, and that's why the works that recently Professor Coutinho has been reporting are so important, is that understanding why and how you can predict the solubility of a compound in an ionic liquid, you can design the ionic liquid. And if you understand very well, as he showed that he can understand now with Cosmo, predict the behavior, predict the Henry constant. You can also predict the Henry constant for the CO2, as I showed you before. So you really can design an ionic liquid that has an excellent selectivity to do the separation. We are showing here the methane. Obviously, this can be done for other gases once you do the work as it has been done here for methane. So designing the solvents is essentially. And we are talking about physisorption, but there is another thing that I hinted briefly before, that is, some ionic liquids can do or can absorb CO2 by another mechanism that is not physisorption, that is chemisorption. And that's what many people have been looking into before. As I showed before, in the Raman spectra, the physisorption of the CO2 on an ionic liquid does not change the spectra of the ionic liquid. But when you have, for instance, bemene acetate, and I use here bemene acetate as an example of the many ionic liquids that can do chemisorption, you really see that the pink bands, the pink spectrum, is very different from the blue spectrum that you have here when you inject CO2. And this is because in this case, oh yes, there is a very strong interaction. It's so strong interaction that it's actually a chemical reaction between the ionic liquid and the CO2. You see here that the CO2 covalently bonds to the ionic liquid that forms a carbene and then reacts. And this is very important. We will be back to that, because here we will be looking into this for the ability to capture CO2. But as you can recognize, there is another ability, that is the ionic liquid can change the CO2, can activate the CO2 for reaction. And this is extremely important when it comes to the other aspect that I won't go into detail, that is the CO2 use, the CO2 conversion into ionic liquids. So we have been looking into that and looking into the importance of this aspect of the chemisorption. And this chemisorption is particularly interesting because as it is a reaction between an acid and a base, obviously it's better when the CO2 is somehow hydrated instead of being dry. So the ionic liquid in presence of water, when it's physisorption, the solvation of the CO2 in the ionic liquid decreases. But when it is the chemisorption, as we showed here, and this is a recent paper, there is an increase, an actual increase of the solubility. And this is very good because more often than not, your effluent as water. because it's an effluent that is resulting of the burning of hydrocarbons. So some amount of water is there. So the ionic liquid will retain the water, and this will be favorable to the reaction with the CO2. You really increase the amount of CO2, and significantly you increase by more than 50% the amount of CO2 that you can retain in presence of water. So water is not a problem when you use chemisorption as it is when you use physisorption. So that's a big advantage. And we studied a number of these ionic liquids where physisorption is present. It depends on the ionic liquid until which range. For instance, the prolinate, you can have chemisorption up to very high concentrations. In some others, it's lower concentrations. This phosphonate one is also very good because up to 0.3 you can have chemisorption. So it depends on the actual stoichiometric reaction, or the stoichiometry of the reaction between the CO2 and the ionic liquid, how far you can go in the chemisorption range. But as I told you, it's not just about capture, it's also about the storage, and it's also more than that about utilization. And I show you how the CO2 becomes activated in presence of the ionic liquid. I have not been working on this field of the CO2 conversion on ionic liquids, but I think it's very, very important, so I mentioned it here. There are a couple of critical reviews, one in Green Chem from 2019, so it's a fairly recent one that I call your attention to if you are interested on this subject, where the authors review all sorts of reactions where CO2 can be hydrogenated, where CO2 can be reducted by electron reduction or other techniques. So there is a number of different approaches that have been carried these days, and the advantage of the ionic liquid is that its presence, it is its presence that allows in many cases these reactions to take place, because it's the complex that forms between the ionic liquid and the CO2 that activates the CO2 to be reactive, because you know how poorly reactive a CO2 is. So the ionic liquid is not only good for the CO2 dissolution, but mostly it can be used for activate the CO2 for reaction. And there is this other very recent review as well on green chemical engineering from 2020 that I bring here not only for its interest. It addresses a number of other types of reactions that were not addressed in the Green Chem review, but because of this graphical abstract, because I like very much this graphical abstract, when I saw this, I realized that many people were thinking in the same lines that we were thinking. And I come back to the CO2 separation from other gases. That is, well, it's clear that you cannot use absorption to separate the CO2, but this does not mean that you cannot use ionic liquids to do CO2 separation. What this means is that you have to use other process units. And one of them that should be attempted is obviously membranes. And that's what we have been looking into. We have been looking into two possibilities to overcome the limits that the transport properties of the ionic liquids impose on its use. I showed you that they are very viscous, and their viscosity makes problems in the transport properties. So to overcome this, you have to increase the contact area between the ionic liquid and the gas. How can you do that? Well, one way is using membrane contactors. The other way we attempt was to encapsulate the ionic liquids. Let me start by the membrane contactor part, because that's something that we have been looking into in the last few years. And the idea is to use two membrane modules. We start with a very conventional one. We bought the 2 membrane models. The way this works is that in one of the membrane modules, you contact the flue gas, so your effluent with CO2 and other compounds with the ionic liquid through the membrane. Then the ionic liquid works as a carrier, and you move the ionic liquid into the second module where you heat it and you release the CO2. So you restore the ionic liquid and you bring it again to the first unit. So the ionic liquid acts as a conveyor belt, taking the CO2 from your gas and releasing the CO2, allowing the separation. And yes, we have been looking to that for quite a while. We create the prototype with some dimension to carry this. We use some ionic liquids with very low viscosity. Look here at 50 degrees, this ionic liquid has a viscosity only of 20 millipascal. That is not very high for an ionic liquid, not very high for a fluid in general, but still it's not perfect to be used for these very, very small tubes of these membranes that have a very, very small diameter, and then it's natural that it causes some troubles to well, the pressure drop is rather high when you flow the ionic liquid through this. So we didn't give up using membranes, but we decided that this was probably not the right way to go. And we had been looking into also microencapsulation. Microencapsulation is a technique that was created by that researcher in Madrid that I mentioned before, Pep Palomar. And we have been working with him and his group for quite some time, and we learned from him and how to prepare these capsules, carbon capsules of that we can fill with ionic liquid. These carbon capsules, they have about 1 micro in diameter, and we get. This is the capsule, as you can see here. The wall has about 150 nanometers, so you can fill these with ionic liquid. You have the capsules. They are porous, so it's very easy for the gases to access the inside of the capsule, and they have very high porosity and very high surface area. So you can fill them very easily with ionic liquid, and they retain very well the ionic liquid in contact with gas. We have never observed, for instance, the leaching of the ionic liquid. And these capsules are really fantastic in terms of the dissolution. They do not change the thermodynamics of the process, as you can see here. When you compare the dissolution in the capsules with the dissolution in the bulk ionic liquid, is exactly the same thing. The capsules, they stabilize the ionic liquid. Here is the ionic liquid degradation temperatures without in bulk. And here is the same ionic liquids now when they are encapsulated, and you really gain up to 40 K in terms of thermal stability, what is very good when you want to work at high temperatures. But the best thing of all is the kinetics. You don't change the thermodynamics, but you change dramatically the kinetics. This is how slowly the gas, the CO2 in this case, penetrates the ionic liquid, and this is how fast it penetrates the ionic. This is in bulk form, this is in the encapsulated form. So instead of taking hours to reach equilibrium, you reach the equilibrium in minutes, because the particles are so small, the surface area is so large that you remove all the obstacles to the mass transfer. So it's really no more a problem that the ionic liquid is viscous, because you really can turn around that problem by using these microcapsules. The problem with microcapsules so far is that you could think about making a monolith or pellets with them, and we haven't been able yet to do that. And we have been trying and looking forward for someone that can compress them in pellets or in a monolith so that they can be used, because you cannot use particles that are that small. They are, as I told you, 1 micron in a fluidized bed, because they would just be even for very low velocities of the gas, they would be transported, because they are so light and so small. So what we have been doing, while we haven't been able to compress these particles into pellets or others that can be used as a filler for a column, we have been trying to merge these 2 approaches that I told you before, membranes and encapsulation. And how does this work? Well, we use these hollow fibers that I showed you before, and we have been incorporating the microcapsules into the membrane by coating the hollow fibers, the surface of the hollow fibers with the capsules. And this can be seen very clearly in this sequence of photographs. This is one of the hollow fibers that is used. And what we are doing is that we are depositing at the exterior surface of these hollow fibers a layer that you can see here, very small layer of these capsules. And this is enough to achieve what we are striving for. In this paper that recently people from my group, Pedro Carvalho and Liliana, published together with the group of KAUST of Professor Susana Nunes, they showed as a first example how they could dehydrate a gas current with this technique of the hollow fibers coated with these nanocapsules, microcapsules. And what you can see here in this graph is a comparison of the performance of these hollow fibers with this particular material with others that had been proposed before. So you have a much higher permeance and a much higher selectivity than most of the current materials that had been described. It's compared to the best one of them. And what Liliana is doing right now, she's at Saudi Arabia at KAUST, trying to do exactly the same thing, but now for CO2 separation and not for water separation, because what we did here was just a water separation. You can know more about this work on this paper in ACS SUSCHEM that was published in the last year. And this is what I had to show you, just the final message. Yes, ILs and DES, they are not good to physical absorption, but they may be used to separate the CO2 from other compounds. But they are designed as solvents, so they must be designed. You cannot just go to the lab and pick the first one that you find in the shelf or pick the first one from the catalog and use it. You have to think about it and to select them. Absorption itself with a liquid phase is not an option. It doesn't work. It's useless to be trying to measure solubilities just for the sake of it, like many people still are doing after being shown for 10 years that absorption is not the way to go. But immobilized support ionic liquids or DES, they may work. The separation can be achieved, as I showed, by membrane-based process, probably also by chromatographic type process, by absorption-like process. And also, I showed you a few results from literature because we are not currently working on that, but that's also an area that is mighty interesting, that is the conversion of CO2. Ionic liquids can activate CO2 to be converted by electroreduction or by hydrogenation or by oxygenation. There are many approaches that can be used and that you can carry the reaction, the conversion of CO2 in ionic liquids, because the ionic liquids are good for that. And I have a special word today for Pedro and Liliana. Pedro has been working with me in this field for the last almost 15 years. And Liliana has been doing this for the last 3 or 4 years, and is now, as I mentioned, in CAUS doing this work. So, final word of thanks for all the group and the magnificent work that they have been doing all these years. And a final word for you as well for your interest and for being here today. Thanks. And now, if you have any questions or any discussion, I will be glad to answer your doubts.
Okay, thank you very much, Professor Coutinho, for very wonderful talk. The high pressure cell reminded my time in Aveiro. Remember when we have a lot of up and down with the gas measurement, but yeah, everything comes in the big picture right now. So I see some familiar name here. I see Pedro, Marcia, Ana Ferreira, the old family when I was there in Pat. So good afternoon from Indonesia. And for others who like to ask question, you can type directly in the chat room, or you can raise hand so you can ask directly to Professor Coutinho. Any question?
Oh, we have Ramesh Kardas here as
Yes, we
well.
also have
Ramesh, good morning, Ramesh.
Good morning, good afternoon. Nice to see you and hear you, João, virtually. And you took us a nice scientific journey from physisorption to chemisorption to membranes and to what you call encapsulates and hybrid things. It's really wonderful. I do not have a question, but I would like to know your views on how far or how close we are industrial application of ionic liquid for CO2, because monoalkanol ethanol amines are still hot favorite, probably IL as a co-solvent, or how we can address the regeneration cost. What are your views? Thank you.
Ramesh, thanks for your question. It is indeed a wonderful question that we all ask ourselves. You know, I suppose you know, that process based on BMIM or C2MIM acetate have been designed and commercialized, although never implemented at industrial scale, for CO2 capture. ProIonics developed a process, and there have been reports on the technical feasibility and even economical feasibility of the process. And we are talking about the chemisorption with a liquid, not with membranes or anything like that. It's just a very conventional approach using BMIM acetate, or I think it was BMIM acetate, as solvent. You can find the life cycle analysis and so on in a paper by Energy and Fuels. So if you want to build a plant, they can build a plant for you. That's not an issue. But so we could have a plant working, operating as soon as anyone wants to pay for that. But nobody wanted yet, because it's always the problem with the new technologies. You have a new technology, it's not good enough that it's just as good as the current technology or slightly better than the current technology, because there is always the people are afraid to invest in technologies that have not been proved into the market. So I think this is one of the issues. Concerning the other approaches of membranes, like we are working on, and other sorts of immobilized for CO2 capture, I don't think we are that close yet. People are still on the lab scale, the demonstrators, and I think we will have at least 1 decade before something leaves the lab, and you can have something at a pilot scale, but a large pilot. I'm not talking about a pilot like we have in the lab with some liters. I'm talking about something that is really big. It will take longer because in this case it's more complex to produce it's not just the fluid itself, it's how to produce the material, how to produce the membranes. So you will have to develop also the technology to produce these membranes in large scale, these hollow fibers in large scale. But eventually this may be feasible. Now you also ask about the possibility of mix these things. I don't think this will be what will happen. I don't think that we will have mixed fluids with amines and ionic liquids. We may come to a new technology based on ionic liquid, but I doubt that we will see formulations with amines and ionic liquids. But that's a feeling, and I may be wrong, and it may happen in a different way.
Thank you. Thank you.
Should I ask a couple of questions here in the chat? How are you calculating pKa of pure ILs? I did not calculate pKa of pure ILs. What I did was to look into the pKa of the acids that were used to produce the bases, the anions. So I looked into the pKa of acetic acid to know the basicity of the acetate. I looked into the pKa of HC dicyanamide. I think it was the dicyanamide that I showed. Yeah, it was dicyanamide. So I looked into the pKa of the corresponding acid to know the basicity of the anion, and that's because that gives you an idea of the basicity of the anions. It's not straightforward to calculate pKa's of ionic liquids, but you can get an idea of the basicity of the ions based on the acidity of the original acids. Now, do you think that capturing CO2 by ionic liquids based on nature of photosynthesis in plants? That's not the capturing, it's the conversion. The capture, if we use something like photosynthesis to do the capture itself, is very bad. Plants are very bad at capture CO2. It's not a huge amount that they can capture. They can capture very small amounts and then they convert it. They are good at converting it, and but not at capturing it. We remove a lot of CO2 because there are plenty of plants and they take a long time to do that. The conversion, can we use something close to the photosynthesis to do the CO2 conversion? That's what many people are looking into. They are striving to do this artificial photosynthesis, and you can find plenty of articles on the artificial photosynthesis in literature. What you can do with the ionic liquids is not that, but it's also at the same time more flexible than that, because you are not restricted to one type. Well, when you do the photosynthesis, you know, there is this reaction of the CO2 with water to form the carbohydrates. With the ionic liquids, people have been striving to do many different things and not just this single reaction. Now, what is more important in building an IS for gas separations membrane technology, cation or anion proper? I think the anion is the most important, but for a matter of price, for a matter of renewability, for a matter of viscosity, transport properties, the cation is also very important. So you have to design it in the two ways. One, what is going to react with water or to strongly interact with water, and the other is how can we complement this with the other properties. So it's not that you have to look just into one of them. Usually the anion is the thing that interacts more with something, but the other is also very important to complement the rest of the properties. Selectivity, why are they very selective? That's the first part of my talk, because for CO2 they have this non-interactive way of absorbing CO2, but they so it's an almost ideal solubility of CO2 in the ionic liquids, and that's why they are not special, but they are good. But they are very bad at interaction. Most ionic liquids are very bad at interacting with hydrocarbons due to their nature, because they are charged species, because they are very polar, and that's why they become very selective. CO2 has not this problem, because CO2 is polar itself, it's quadrupolar, so he has no problem of interacting with something that is polar, also like an ionic liquid. But methane or ethane, they hate to interact with something that is very polar, like an ionic liquid that has electrostatic charges, and that's what creates this great selectivity that you cannot achieve with many other solvents, because they are not as polar or charged as the ionic liquid. So the nature of ionic liquid is very good to separate CO2 from other things, not from water, but as I showed you, the water itself can improve the CO2 absorption into the ionic liquid, depending on ionic liquid, obviously, but it can be good. But then the separation from other gases like nitrogen, like methane, like ethane, other hydrocarbons, or other things that may be present on flue gas, they are very good at that. Is there any factory or house industry that uses ionic liquid on process? Yes. Recently, last year, there was a paper about industrial applications of ionic liquids by, oh, I forgot the name.
I think BASF is ionic liquid for some reaction as acid catalyst. From
oh yeah, no, but it's not one example. This book by
Mark
do you
Schifflet.
remember the name of that person that worked in DuPont that is now
Schifflet,
in
Mark Schifflet.
Mark Schifflet. Thank
Mark
you,
Schifflet.
Ramesh. Mark Schifflet. Mark Schifflet published a wonderful book where there is one chapter by the person in charge of proionics just on listing the industrial applications of ionic liquids. There are maybe 50 different industrial applications right now of ionic liquids on the market, not for CO2 capture, but for many other applications that are already being used in small scale or large scale. Probably many people do not know, but in some mobile phones, cell phones, you have ionic liquids on the screen because of their liquid crystalline properties and so on. There are plenty of applications these days. I really recommend this book by Mark Schifflet on industrial applications of ionic liquids for those that doubt that ionic liquids will ever reach the market. And there is not by BASF, but there is an UOP process for hydroformylation that is based on ionic liquids, and we are talking about a petrochemical process, very large scale, that is based on ionic liquids. And is there any metal, some kind of material that works well with ionic liquids? I don't know about this, so I won't try to answer what I don't know about. Is there any specific structural formula? Yes, that's what I was trying to convey. There are a number of thumb rules, or you can use models like COSMO to try to design the ionic liquid to optimize it for not only for CO2 capture and separation, but for many other applications. I recommend strongly the use of COSMO as the tool to design and select ionic liquids. It's not a perfect tool, but it's a good tool, and if you learn how to use it, it can really provide you many informations. Commercial Applications of Ionic Liquids by Mark Shiflett. That's the book. Thanks, Ramesh. Other questions besides those on the chat?
Okay, if there is still any question, if you want to ask Professor Coutinho directly, you may raise your hand using the emoji here in the reaction. Anyone have more question for Professor Coutinho?
I think we are done here.
Okay. Okay, maybe. Okay, let's see if there is no more question. Okay, we still have one more question. Is it useful for gas hydrate formation?
It is useful for gas hydrate formation. I didn't address this issue here, but there are some quaternary ammonium N444 that are used to enhance the production of what they call hemihydrates. You can find this on literature. You can also use them to the other thing, that is to prevent hydrate formation. So you can, depending on the ionic liquid, you can use it to prevent or can use it to enhance the hydrate formation. This has been studied. You will find results on literature for that if you look for ionic liquid or quaternary ammonium and hydrates. And I really thank you for your interest on my talk, and I would like to stress Ramesh experience, Kiki experience. The doors of our lab are always open for collaborations. So if any one of you has interest to visit us, to engage and work with us, just send an email to start a discussion, and we will be more than glad to start doing things along with you. It's really a pleasure. That's always been a pleasure for us to work with other people, and that's what we want to continue to do.
Okay, thank you very much, Professor. Okay, because there is no more question from the audience, maybe Dr. Rino would like to add something before we close the session.
Yes, can you maybe stop the screen?
Certainly.
Yes, on behalf of LPPM ITB, we would like to thank Prof. Coutinho for his time, sharing his knowledge, very important topics about the CO2 capture by the ionic liquids. Hope we can still learn from you, Prof. And then hopefully many of our colleagues at ITB can collaborate with your institutions, because I saw that you mentioned there is a research center focusing on several topics, and at ITB we also have many research centers that can match with your interest. Perhaps we can collaborate in the future. In the end of the year, we normally open call for proposals, so the ITB researchers can apply a research grant from ITB, funded by ITB, and then he can add the collaborators from the Portugal, or maybe from your groups. So hopefully we can have a matchmaking between ITB and the Portugal in your place, Aveiro. So thank you, Dr. Kiki, also for organizing this event. and also our colleagues who attended this meeting in the afternoon. So we really thank for your coming, and see you in the next event. Thank you, Dr. Kiki. I give back to you.
Okay, thank you very much, Dr. Dino. And to close this FGD session, I would like to thank Professor Coutinho again to share the knowledge on the CO2 capture and conversion. Hopefully, this will be start new collaboration between Universidade de Aveiro and ITB. And I also like to thank you for the all audience for the active participation. Thank you very much, and see you in the next FGD session. Thank you very much, sir.
We can take a photo together.
Thank you.
Okay, sure. Maybe.
Sure.
Okay.
Please open the Zoom camera.
Okay, please open your Zoom camera.
Okay, from our staff, maybe you can help with taking a photo, Pak Ali or Pak Yanto. Okay, so it will be captured by our staff. Okay, maybe some of the sign code, some code. 1, 2, 3.
1, 2, 3. Again, Pak. 1, 2, 3.
Once more.
Okay, thank you, Pak.
Okay, thank you very much, everyone. Have a nice evening for those in Indonesia, and happy Friday for those in Portugal. Like I said, free day.
Thanks.
This session. Bye-bye.
Bye-bye.
Province mana?
Ya, Bang Fix mana?